Given two functions f and g from R to Rm, notice that f of x and g of x are both elements of Rm. Therefore, it is possible to add the two elements f of x and g of x. It is also possible to take the scalar multiple of f of x, and finally it is possible to take the inner product of f of x and g of x. These three operations on vectors in Rm gives us three different functions from R to Rm. Namely, we can consider the functions f plus g from R to Rm defined as f plus g of x is equal to f of x plus g of x. Similarly, cf is a function from R to Rm defined as cf of x is equal to c times f of x. And finally, f dot g is a function from R to R defined as f dot g of x is equal to f of x dot g of x. Now, when we studied functions f from R to R, we knew that sum, product, etc. behaved well with respect to continuity. We want to now show that these results hold even when we study functions from R to R. Let us prove these one by one. First, we will look at the sum of two functions. The theorem states that if f and g are differentiable at c, then f plus g is differentiable at c, and the derivative of f plus g is equal to the derivative of f plus the derivative of g. And the proof of this fact is quite simple. Notice that f of x could be written as f1 of x, f2 of x, etc. up to fm of x. And similarly, g of x can also be written as g1 of x, g2 of x, etc. up to gm of x. Therefore, f plus g of x, which is equal to f of x plus g of x, is equal to f1 of x plus g1 of x, f2 of x plus g2 of x, plus etc. up to fm of x plus gm of x. Now recall that a function is differentiable if and only if all its components are differentiable. Therefore, as f is differentiable, we know that each of the fi's are differentiable. As g is differentiable, we know that each of the gi's are differentiable. Therefore, fi plus gi is differentiable from the similar theorem for functions from R to R. Therefore, fi plus gi is differentiable for all I. Therefore, f plus g also has to be differentiable. Further, we know that the derivative of f plus g at the point C is equal to the derivative of f1 plus g1 at the point C, the derivative of f2 plus g2 at the point C, etc. up to the derivative of fm plus gm at the point C. But from the theorem for functions from R to R, we know that f1 plus g1 dash is equal to f1 dash of c plus g1 dash of c, and so on up to fm plus gm dash at c is equal to fm dash of c plus gm dash of c, which is equal to f1 dash of c, f2 dash of c, etc. up to fm dash of c plus g1 dash of c, g2 dash of c, etc. up to gm dash of c. Now notice that the first term is f dash at c and the second term is g dash at c. And therefore, we have this result. Similarly, if f is a function from R to Rm that is differentiable at c, and alpha is a real number, then alpha f is also differentiable at c. Moreover, the derivative of alpha f at c is equal to alpha times the derivative of f at c. The proof of this result is exactly analogous to what we saw earlier. Therefore, I leave the proof as an exercise. Finally, we look at the dot product of two curves. If f and g are differentiable at C, then f dot g, which is a function from R to R, is also differentiable at C. Moreover, f dot g dash at C is equal to f of C dot g dash of C plus f dash of C dot g of C. This is an analog of the Leibniz rule, and the proof is an application of Leibniz rule to each of the component functions. Notice that f of x dot g of x is equal to f1 of x into g1 of x plus f2 of x into g2 of x plus etc. up to fm of x into gm of x. And this is true for all x. Therefore, you can notice that f dot g is equal to f1 g1 plus f2 g2 plus etc. up to fm gm. Recall, we had seen that f is differentiable at a point C if and only if fi is differentiable at the point for all I. Similarly, g is differentiable at a point C if and only if gi is differentiable at that point C for all I. Therefore, as we know that f and g are differentiable at C, fi and gi are differentiable for all I. Therefore, fi into gi is differentiable at C. And as this is true for all I, the sum of these functions, namely f1g1 plus f2g2 plus etc. up to fmgm, has to be differentiable. In other words, f dot g has to be differentiable. Moreover, f dot g dash at C is equal to f1g1 dash at C plus f2d2 dash at C plus etc. up to fmgm dash at C. The proof can now be completed by applying the Leibniz rule to the products f1g1, f2g2, etc. up to fmgm. And I leave that part as an exercise.